Okay, good afternoon, everyone. The goal of this lecture is to introduce a couple of tools that you may find interesting for your simulations, for any experiments you need to run. First, I will briefly introduce bash scripting, just the basics we need for some scripts I saw in the end, just some basic stuff. And then I will get into the makefiles, and then in the end I will put together both things into an example. I will go bit fast. It's going to be brief, so if you have any question or want me to spend more time on something, just let me know. So what's the problem we're addressing here? So usually we have to run many tests. So if you have some code we want to run, we try different sizes or different libraries, different number of threads. So we have to run many of them. Then maybe you want to manipulate the results automatically, just get some columns or skip some rows, for instance. And then, for instance, plotting, visualizing the results, and so on. So what we want to do is to write some script. You run your simulations. Then you just go to bed, just do something else. And then when you come back, you have your results. You can visualize the figures, or you can just manipulate the data as you want. I will start with some basic commands, not even all of them, just working with directories and files. Then redirecting input and output or standard error and pipes so that we can connect input and output from different processes. And a bit of wildcards, we will see what that means. And then I will get into control structures, just briefly if, while, and for. As you can see, it's basically as any language. If condition, then something else, otherwise another condition, different code, and so on. While condition, do something, and for some elements, do something else. So, can you see this, or maybe bigger? That better? Okay. So first, basic. For instance, we may want to change directories. You may want to create directories. For instance, this creates a directory. Make directory. You can change to that directory. You can list it. So you list the contents of the directory. There's nothing now. We can create a file. I will explain this one later. Now you list the directory, you have some files in there. You may want to rename them, for instance, file to another. Now you have this new name, you may want to copy it. Now you have both. You may want to remove these files, for instance, this one. Yes, to remove it. And this sort of things. Touch, the one I use first, it does two things. So, first, you can list the directory and also get some more information. So you can have long listing where you have user, the owner, and the group, date of last modification, some permissions. You may also you don't see it there, the hidden files, dot and double dot, which means this directory and the parent directory, or recursively I will show later. So this touch command I just used up there can do a couple of things. If the file doesn't exist, it creates it. So now we have this new file, and it has some date, last access or modification, I'm not sure. If you do this touch with copy, since it exists, it updates the last modification access. So instead of 507, now it's 508. I'm just telling you this because then I will use it in the makefiles. Also, just couple more echo, just display some string. if you use -n as an option, it doesn't print the end of line, which might be useful if you want to, for instance, create an empty file. You can use simply this. Let me call it empty. And what I just did with that symbol greater than, it's just redirecting. What echo displays, it goes into a file. So now we have an empty file. Cat means cat just displays in the standard output the contents of the file. Also, you can do something like some file, and now you have the content of that file. For instance, you can append with a double greater than, and now you have both lines in there. That's redirecting the standard output, and you can also redirect the standard error. For instance, if you list something that doesn't exist, it's going to give you an error, and you can redirect this into some error file. And it's over there, and you don't see it in the screen. It just goes directly there. You can also append, like with the standard output. Now you have it twice. And you can also redirect the standard input. So if there is a program that reads from the standard input, you can pass a file, just pass the contents, and then the program will process it. For instance, cat, if you don't pass any argument, it reads from the standard input, and what you read, it writes in the standard output. So you write something, it prints it out. You write something else, and it does the same. If you have this file, you can also redirect the content of a different file to the standard input of cat. We'll get this file, and we'll print it out to the standard output. So you get these same two lines. This is the basic redirections of a standard input and output and error that you can do. Now there is a thing called pipe that allows you to connect the output of a process to the input of another one. So if you, for instance, have a file with numbers, its line has a number 1 to 15. You can do the following. For instance, if you want to get line 6 to 10, you can use the head command that takes n lines from the beginning, which is, first 10 lines. And then you can redirect the output of this command to the input of a different one, which, for instance, may be cat you will not see, maybe tail. Okay. This command, instead of head, the first n lines takes from the bottom n lines. From whatever is in the standard input, prints it out. So if you want to get 6 to 10, you want the last 5. So you pass this 10 from head to tail, and tail gets the last 5. So you're connecting the standard output of head to the standard input of tail. Okay, this is probably the basics about file manipulation and input and output. And a couple more things before the wildcards. You may run more than one command, like in a sequence of commands. Like you may want to list and then cut the file, so you can do both. First it lists what you have, a directory and a file, and then it got just display some file. You can also do it this way. You can say and, so you do both things. The difference is that if you use the semicolon, it executes always both commands, ls and then cat. But if you do and, it only executes the second if the first didn't give an error. So as you saw before, if I say this, ls gives an error. So it doesn't execute the second one. But if we do it this way, it does both. How does the cell know whether it returned an error or not? Well, there is a variable, a built-in variable in bus that tells you what was the returning value of the function. Like if you write some C program and then in the end you say return 0, that 0 is the one that will get into this variable, which is $? This 0 comes from cat. It didn't give an error, so 0 means no error, means true for bus. It's different from C in that case, in that sense. If we do something wrong, gives an error, gives you a different value. Usually, if you have some problem with some command, you can check that value and then maybe look at the documentation and see why it happened. Come on. Whatever. And this return value will be useful later on. Okay. And just to finish with this basic stuff, we have the wildcards. Let me go somewhere else to solve this. Do we have, yeah, okay. So we have the star, the asterisk, which means anything that starts with makefile and then continues anything, which in this case is makefile, empty, or makefile 2, makefile 3, but not main. If we do this, it gets main because all of them start with MA. We have the question mark, which takes only one character, which in this case is 2 or 3, but not empty, so makefile alone is not taken. You can use the square brackets to specify which ones you want to take. So it could be makefile 2 or makefile 3, or only one of them, or the other, for instance. And also you can use the curly brackets to specify, instead of just one chart, you can use strings. So you could say, you can specify, for instance, suffixes of files. So for this case, you can use 2 or 3. Or if you go here, you see, for instance, you have all these files that start with makefile. They have different endings. And you may want to remove some of them, like those, I don't know, for instance. So this takes all the files that start with makefile dot and then one of these extensions. And then with remove, we remove a file, so we can remove all of them. This is useful together with the F option so that it forces it. For instance, these two, it doesn't ask, so you just remove them.
You can put a star instead of a makefile.
Yeah, I could. For instance, well, we can do the following. There are these two with the S and M ending, so you can actually remove anything with that extension, and then both are gone. They're not there anymore. Okay, these are the basic commands I wanted to show, and then just to mention some environment variables that might be useful. Some of them are set at the startup. For instance, home, always with a dollar in front, so any, yeah, better like this. Variables in Bash scripting, all they start with a dollar and then the identifier. Home is built-in, and it just includes the path to your home directory, which in my case is just home and my username. And another important one is path, which is the list of directories where the system will look for an executable when you want to run a command. And here I have the classic user, local bean, user bean, and so on, and then a couple more in my home directory where I can install my own programs. Okay. So these are commands you just type on a cell, but maybe you want to put just a sequence of them to perform something more interesting. You can put them in a script and then execute a series of these commands. For instance, here we have just some variables. Okay, this is an example of variable use. First of all, we have the cbang line, which tells the system which program will execute this script. In this case, it's Bash, so we use that line. It always starts with greet and exclamation mark, and then you put the path to the program that will execute it. In this case, it's that. You can use user bean Python for Python scripts or anything else for Perl, whatever.
Question?
Sure.
So this is necessary.
Sorry?
That you print a path to the program that is executing the script.
Yeah.
Ah, okay. Even though it's starting with how is it called, star?
cbang.
Yeah, the greet and the exclamation mark. That's how you specify. If that's in the first line, the system will look for that string to execute it. So you could have also a path to Python if it's a Python script, or Perl, something like that.
Or path to end, which would be more.
Yeah, user being env, and then, yeah. But usually for Bash you use this one. Or I do, and it works. But yeah, you can also do something like this. Right? That's what you're trying to say. Yeah. This, I'm not sure how it works, but it just knows where the program is.
System specific, and knows where the path to the,
Yeah.
to the right path.
So this is like more portable if you go from architecture to architecture. I do that for Python, but usually Bash it's in the same place. But you're right, thanks. You can of course have variables, like some numeric variables here. The greet indicates the starting of a comment. So it can be at the beginning of a line, and then the whole line is a comment, or just in the middle, and from there to the end, the whole line is just, from the greet till the end is a comment. We set here some variables with some values, and then we can perform some basic math. Can you see it? Yeah, I guess. Okay, I'll tell you what it says. It's just an operation, basic math. So it takes variable 2, subtracts variable 1, and divides by variable 3. To do this, you do, for instance, dollar, bracket, bracket, and end up with double bracket as well. And then you just echo, so you print this string. Wherever you find this dollar variable, you print the value of the variable. The rest is just a string. So it will put the operation, and then the result will print. So now you can, what is it? This one. So it says, okay, this is the operation you're performing, and that's the result. But for that, you need to use the double quotes. Otherwise, the variable is not replaced with the value. So if you do it this way with single quotes, it just gives you the whole string. It doesn't replace with the values of the variables. And a little bit on arguments. You can pass arguments to the scripts. There are a bunch of built-in variables. that are set when you call the script. $grid stores the number of arguments, including, does it? I think it includes the name of the executable. I'm not sure right now. 1, 2, 3, 4 is first, second, third argument of the script. At gets all of them from 1 till the end, so it skips 0, which is the name of the script itself. Here we can just call it and.
One question.
Sure.
To the example before the last one, if you do some
Here?
yeah, error stuff like division by 0, will we get some warnings or errors?
We can try. I don't know. I guess it's going to give an error. Yeah,
Oh, okay.
it complains.
Do you have this script modded as executable? Because then the hashbang would be used instead of just something.
Yeah. So if it's not executable, you can do sh or bus or just some cell to execute it. Probably it should be bus in this case. Anyway, so you can not set the permissions and execute it, or you can set the permissions, which is this way. You say with +x, you tell you add the permission, you make the file executable. So now, if you look at this here, you have an X, and it turns green to tell you it's an executable, and you can do that. And now, since you don't tell it which program, which interpreter will execute it, it uses the cbang line and goes for bus in this case. So, okay. Can pass my name here and number of other arguments, and it says you passed 4, which are this string here, and then A, B, and C, and then just gives me the line I used to execute it, which comes from sgrid tells how many I passed, which then it doesn't include the name of the script, and then I just print the first one and then all the list of them. Notice that there is a difference with using the double quotes or not. So if we don't use it here, the first argument is only my name, and I pass 5 of them. So if you want to pass some string with spaces in between, you just have to use the double quotes. Probably that's enough. Let's see. Okay. One more command, which is test, which is used to compare strings, compare numbers. For instance, you can say, is 3 equal to 3? And it gives you the answer in this variable, which says, sure, it is. But if it's not, it gives you a different number. So this program tells you if it's true, if the condition is true, it gives you a 0, returns a 0, which is the value for true in bus. If it's different, it's false, gives you a different number. It's different from C. This you can also, I don't know if you can do it here in the cell, I don't remember. This is an alternative syntax for the program. If you do that, and this is usually used for if statements or while loops. And just a quick overview of this control structures. This is pretty similar to any other language, so we'll just go through it. Let me start with numerics, maybe. It says if you pass an argument, if you pass n arguments So if you pass 2 of them, if it's not equal to that, meaning 1, 3, 4, any other, it will complain, I want 2 of them, and will exit. Otherwise, it says, okay, if these 2, one is greater than the other, print this. If it's less than the other, print the other string. So I guess you get the idea. For instance, you pass 2 and 3 and says 2 is smaller than 3, or the opposite. So just the syntax is like here now. So if condition, then something, otherwise something else, or you can just put a sequence if, else if, else if. And these 3 options, you have the previous ones to compare numbers. These ones, for instance, check whether a file exists with -e, or if it's a regular file or a directory, if it's executable. So you have a number of options to check if files exist, they're executable, and so on. And, well, just while loops are the same. While some condition, do something. The examples will all be uploaded, so just to show you that they exist and you can use them. Like for loops, so you use the iterator and then a sequence of values that the iterator will take. For instance, that. And it says, okay, 1, 2, and 3. And one other command I will use, and this is specific for Bash, or at least it's not in every cell, is the command seek that gives you generates a sequence. This is the minimum value, this is the maximum value, and the one in the middle is the increment. So it will generate from 100 to 1,000 in steps of 100. And the back quotes mean return the string generated by this command. So it generates a string 100 to 1,000 in steps of 100, and it's the values that the for loop will take. So something like that. You execute something passing a different argument from 100 to 1,000. No need for functions. So this is more or less the basics I wanted to show, so that we can then apply them to some script to run some experiments. So let me go back here and start with the makefiles. What I want to do now is just give you an overview of the make program and how to write makefiles to automate, in general, compilations of the automatic compilation of programs. So the idea is that, in general, when we write our code, we have our projects, we have more than one file, hopefully, and in, I don't know, 6, 10, 1,000 of them, whatever. Then if you do it one by one, it's really annoying, like GCC blah, like a long list. And then if you update one of the files, in general, you don't need to recompile the whole story, but maybe only one and then link to generate the executable, or a couple of them, for instance. So imagine you have, this is your source code, have a bunch of .c.h files, so modules, fgls, chol, lski, eigen, input, output, couple of headers with the libraries, BLAS and LAPACK, and then a driver file. So you should go, if you do it by hand, you go one by one, GCC, blah, to generate an object file, to generate another one, 6 of them, and then you link all together. Plus, you usually need some flags to specify symbols, to specify directories with include files, the headers. Same for libraries, you specify paths, you specify the libraries. So it's a lot of writing. One nice option to solve this problem is using make and makefiles, so that you can automate the compilation of the program. You tell make what to do, how to compile the program, and not only it compiles the program, it manages the dependencies. So if you specify which object depends on which other, and you modify one, it will not recompile the whole project, but only the ones that need to be recompiled that depend on this one that probably changed. So in the previous one, these are the files we had in the upper part. Every pair.c.h is compiled into an object file. Then there are dependencies among them. Just the arrows might seem a little bit confusing. So these dependencies are only from the header file. So FGLS, Cholesky, and Eigen depend on all these header files. So if you modify io.h, you have to recompile the two on top and also driver, actually. And then when all these objects are, these .o files are created, you put them all together and link them with some other libraries you may need, and you obtain your executable, your driver. So this reflects the dependencies that make will build, and depending on what you modify, you will decide whether you need to recompile just one or two files, or you need to recompile the whole thing, and it will do it automatically so that you don't have to remember what you need to or not. So as I said, it determines automatically which pieces of a program you need to recompile. It issues the commands to recompile them in general compilation. You need to write makefiles, which you can see it as just a sequence of rules that tell make how to compile each object and then link them together and do other stuff. And then once you have the makefile, you just type make on a cell, and it does it for you. And it's not limited to programs, although I will just focus on that. You can do more stuff. Anything that has these dependencies and needs to manage it, you can do it through makefiles. Okay, so this is the basic unit of information you put in a makefile, which is a rule. The rule, in general, is formed by a target, the file, the object you want to create, a series of prerequisites or dependencies, so the object you need in order to build the target, and then you specify this sequence of commands that you need to create this target file from the dependencies. So first example, just to see what it's doing, it's just a little program that calls the gem. This is just initialization and so on, and calls the gem. I think that's what you saw last class, just matrix multiplication. So it just initializes and then calls it number of times, takes some timing, and prints out some gigaflops per second, some performance numbers. So first basic makefile. Well, you want to create the executable, main.x. It depends on main.c, the source file I just saw, and that's the line to compile it. You say, okay, get main.c and generate main.x, just compile it. So, well, the makefiles in general, you name them like that, makefile or with capital M. These are the two names that make will look for if I just type make. First error, there is something you have to remember. This is not a set of spaces. It's actually a tab. So it has to be like that. If it's not a tab, it will complain, as stupid as it seems. Okay, now, tries to compile, but it doesn't find the code that actually implements the function. So we need to specify where this thing is. I think you saw this already last time. So this is the path to where the library is. This is the, oh well, just it's a static one. This is the library. So now you give the compiler the implementation, the object where the gem is defined. Oh, nice. Okay, we need one more library. Forgot. Yep. And it just compiles it as expected. It just executes the line we told him to execute. And now you just do it. It expects some arguments. It's not transpose, nor transpose, just do it once. And it gives you some gigaflops per second. Now, what else? We may want to specify some other rules to clean up. For instance, if we want to remove the object files or the executable, if we're preparing some tarball, so that you just release some code or you send it to someone, you don't need to specify all the object files and the executable, just send the source code. You can use rule like this one. If there's no dependency, no prerequisite, it's always executed. So this clean rule will always be executed. Now, if we type, you want to execute this make file, which is not the expected name, you can say, okay, use this file. And now we'll use makefile 2. If you execute it, it goes for the first rule, which is clean. And usually that's not what you want. You want it to compile. So you can do two things. The idea is that make goes through the list of rules and takes the first one as the default. That's why it's executing clean. So one thing you can do is just to put it behind, so below main X, and it will execute main X. Or you can tell make that you want the other one to be the default. And now it compiles the code instead of executing clean. Yep.
Do me a favor and create a file clean, and then you will probably figure out that it will not always build if there are no prerequisites, but it will always build if the file clean does not exist.
Yeah, that's coming now. Thank you. So you usually use, so that's what your colleague said. If it's not true that it's always executed, if there's no prerequisite, for instance, if I create this file and I say execute the rule clean, it will say, okay, there's nothing to do because clean is there. There's no prerequisite, I'm done. To specify the rule you want to execute, instead of the default one, you specify the name of the rule. So if it's clean, you say make clean. If it's make library, it's make library, and so on. To avoid this,
Make main.x would be like.
sorry?
Main.x, you could say make main.x.
Yeah, sure. So to avoid this confusion, you can say, okay, clean is a virtual rule, it's a virtual target. So it doesn't matter if there is a file with that name, just execute it. So this way you avoid the confusion with having files with the name of the rules, which you want to be executed all the time. Now, instead of getting the source code and generating the executable, we may want to generate first the object file and then link it to generate the executable. So when you have this sequence of rules, make works recursively. So it goes to main.x, which is the default goal, sees that there is a dependency, which is main.o, and then checks whether it has to do something with that rule. So it comes here, sees that there is a rule to build main.o, And at the beginning, when nothing is done, it says, okay, this main.c exists, let me build main.o, and executes that command. So if you allow me to do this, it first builds the object and then links together to get the executable. Now, if we do it again, it realizes that main O is updated, so the timestamp is in the past, meaning the last access, last generation of the file. So it means it's updated, nothing changed. If we do the following, now the make will think that main.c has been changed, and then we'll realize, okay, main.o is not updated, so I have to build this object, and then since main.o will be again not updated, has to execute the rule again and recompile it and link together to get the object, the executable. Oh, this is not the right one, sorry. Okay, let's start over. We compile it, we touch it, and we do it again. And now it says, okay, it's been modified, so I have to recompile to get the object, and then since the object is new, I have to relink them to build the executable.
One question.
Yep.
Could you repeat what this phony does in the
Sure. So, as a general rule, if you have one target without dependencies, it will be executed all the time. Now, if clean exists as a file, it will think that the file exists, it's up to date, you don't have to do anything. To avoid this, if clean is a different story, it's completely different from the file, you really want this to happen, to be executed all the time, you do that, you say .funny, and then you say, specify a list of virtual targets, sort of speak.
So this means that what comes after phony means it's definitely a rule, not a file.
Yeah, so it means, I don't care if there is a file named clean, just do it.
Okay.
Just ignore whatever is there.
Just to avoid the conflicts between
Yeah.
the names of the rules
And the
file
files
names.
in the file system.
This could be a useful thing if, for example, you want to download a file, then you don't have any dependencies. You can't put a dependency on a URL or something, so you would have no dependencies. It would do your wget, you would have the file, and then it wouldn't do it next time again, if you were to leave the phony out.
Thanks. Okay, one more example. This is the one I just saw in the slide. So we have a number of files, .c, .h, and so on. Let me get rid of this. So if you do it as we've done so far, just putting everything together, it's awful. You see it, right? So you have rules for the binary, and you have rules for every object with dependencies and so on. Simply crazy. Okay, so just ignore it. Just think of it, it's just, you don't want to do this. Okay, so how can you make it simpler? Okay, first we can use variables to simplify it, to make it more readable. You may use variables for directories, like where is the source, where I want to put the executable, which are the objects, and so on. And then you can use variables for the compilation stuff, compiler, flags, libraries, include directories, and so on. So what we have here, okay. First thing you notice, there is this all here. And this is something I usually use instead of the default goal. I just say, okay, I always put all just to give it a name at the beginning. It's not that I do it, people do it. And you specify, when you just type make, all the commands you want to actually be executed. You put it the first, that becomes the default, and then just execute the rest if it's part of the dependency. So in this case, there is a directory for the sources. I want the driver, the executable to be in a different directory, which is this bin directory. So first I build it, and then I compile and put the binary there. So there is this rule to build a directory, which is, just remember, this is the test command. This is saying, if this thing exists, it's a directory, do nothing. If it's not, then you create a directory. It's just a logical OR. It's just a shortcut. So if it doesn't exist, if it's false, it will go and evaluate the other one. If it's true, the whole thing is true and doesn't get there. And this at in front is simply saying, don't display this command in the output. So before, when I typed make, all the commands were output. If you put that in front, it doesn't print this one. And then we simplified a bit the previous make file. We say, okay, now instead of the list of objects, we have a variable that says, okay, these are all the objects. I said that at the beginning. So these are the dependencies. Compile it with this compiler using these flags, all these objects and libraries, and generate the executable. And then for each object file, again, these are the dependencies, which is the C file, and then all the possible header files on which the target depend. And you have a similar line for every object, using now the variables for the compilation, CC and C flags, which is these two things up here, compiler and this flag. Instead of having all these repeated all the time, you just make it more readable. And then you have, again, the clean rule that removes the objects and the executable. Okay, so that's the first step to make it a bit cleaner. You use variables and everything gets all of a sudden a bit more readable. Next, what one can do is, instead of having one of these entries for every object, can use the how is it called, automatic variables, which are built-in variables that creates by itself when executes a rule. For instance, $@ means the target of the rule. The less than means only the first of the list of prerequisites, and then the head means all of them. So what one can do is to use this pattern rule that says, okay, whenever you need to build .o, if you have a file with the same prefix and ending in .c, which means I have a C file, I want to create the object file, you can execute this rule, which is compiler and flags, then the first, in this case, only prerequisite, which is the source file. You compile it and get this object file, so the output goes to the name of the target. The idea here is that we have all these objects up here, and then when you want to build the executable, you have this list of objects. So the make will realize that it needs to build all these objects, and says, okay, how do I build these ones? Since there is no specific rule and there is this pattern rule, it will say, okay, every object file, I have the C file, okay, I compile it and generate the object, and then you can skip all those lines. But you still want to specify dependencies, so you can do it in different lines. You can specify dependencies in some line and the compilation in a different line. So basically, these three on the bottom just depend on themselves, the C and .h. The others have some other dependencies on the header files. And then just the clean up rule. So let me actually then execute the one before. Really. Just let me execute this and see what happens. So it's as expected. Let me remove a line here that makes it less readable. Oops. Okay, so it goes through every .c file and generates the .o with the same compiler, the variable we set, the series of flags, and then in the last line it links all the objects, puts them together with the libraries, and builds the object file. Okay. Also, we don't even need to specify that rule here, the pattern rule, because this is defined by default in make. So if you don't specify the rule to build an object file, it will try to apply default rules it has, like for instance, from a C file building the object file. So if you define properly CC and C flags, for instance, it will just execute this line by default. You still have to specify dependencies. The rest is the same as before. Okay, so now we execute this last one and it does exactly the same. So you don't need to put this pattern rule. And then one last more thing we can do is, well, you might have thought about this. You could actually say, okay, source directory star like a wildcard and .o, so you get all of them and you have to type them. Problem is, in general, the wildcards don't get expanded when you set a variable, so you cannot do it. You cannot do simply something like this. So you can use built-in functions from make. For instance, wildcard says, okay, all the files that give me in a string, a list of the files that match this pattern. Oh, I see. So this gives you all these sources. It says, okay, the source directory, every .c file, it's put in a list, and that goes into the variable sources. And now you can use pattern substitution to say, okay, now from this string here, just replace. So it finds all the entries in the list that have this some stem, the root, whatever, .c, and replace it with the same prefix .o, and that becomes the list of objects. Alternatively, you can do it this way. It's just a shortcut. So from sources, everything ending in .c, give me .o.
Question.
Sure.
So this wildcard is kind of command.
It's called function in make.
Okay.
It's a function that says, okay, yeah, expand this and give me everything that matches the pattern. It's similar to what we saw before in Bash.
Okay, so after the wildcard there has to be something that includes a star. So if
Well, you can just say a file. You don't need necessarily to put a star, but you can use this star as a wildcard, for instance. So you can say in this directory all the ones that end with .c. I never tried with question mark, for instance. I guess it does it. I don't know.
okay.
So the meaning is more or less the same as with Bash scripting. And then this is an alternative for the second line for the objects. It's exactly doing the same. And the rest remains. And then one detail here that can make your life easier as well. So all this list of dependencies. So what do? You go file by file looking at the include to see whether you're including this .h or that .h, what do you depend on. So you usually don't just go and build a diagram by yourself, a graph. So one thing you can do, at least in GCC, I'm not sure with Intel. So if you do, something like that. So you pass all the C files and tell him, give the option it will generate this list of dependencies. So you get from common, you have C and H, the driver depends on many more. That's a shortcut. Probably there are more sophisticated ways, and you can use much more complex tools, but as an example, it works, and you just can paste it or just automate it in some different way. And it's just doing the same as everyone. Gets all the objects, compiles them, and links them into a binary file. Well, not much actually. So sometimes you may be using different architectures or computers, whatever. You might be running your tests in the cluster, RC cluster, or maybe in your computer or in your office, different architectures, compilers, operating systems, whatever. One of the ways to simplify the compilation, depending on what you are, there are several. The one I'm using, for instance, for this code, is to specify the options that are common to every architecture, like the compiler, or not even the compiler, just some flags, or where the include files are. So give me all the warnings, or independently of where I am, I want to link with this library, for instance, or where the sources are, where to store the binary. And then the rest of information you can just grab from a file.
One question.
Sure.
Can we make a target for that file so that it does the dependencies automatically builds its dependencies and then includes them? Is that possible?
I guess I've never done, but I've seen pretty complex many files that do these things, but I think it's not necessary to get there for this. So
Yeah, I've seen it.
I think it is. So just go for it. I'm just showing the basics so that you can just run your experiments. Something more advanced, there's a lot of documentation online or books, so no problem. And then in these files, for instance, you can have a bunch of them. This is going to specify the options if I want to use GCC with GotoBlast, for instance. So I say, okay, this is the compiler I want. These are the libraries I want to link to. So LAPACK and Goto, and then other libraries needed by LAPACK and Goto. Also, sometimes the flags for OpenMP also change from compiler to compiler. Or for you may want to use GCC but with a different library. So you use MKL and you have different paths, for instance. So you can just grab one of these files you have for different places, and depending on where you are, you can pick one or the other. You can also put it inside the makefile. You can have conditional compilation and so on. But it's just a way to do it. This one, I think, is Goto with GCC. And it just does the same as with all the previous examples. Uses GCC to compile all the C files into object files. Uses GCC with LAPACK and Goto to build the executable. Okay. Now, this is again the same example, I think. Yeah, So the one I saw at the beginning, the one that calls gem number of times. Now I want to show that it's not only C, you can actually use it for Fortran code, for instance, and then you can compile them together. You can have Fortran code, C code, you can put it together in some binary. In fact, some of these libraries, numerical libraries, are actually written in Fortran, although I'm using C all the time. So first one's just pretty basic. You specify options for both C and Fortran. You use Fortran to compile the Fortran code. You use gfortran, and you use GCC for C code. They all generate object files, and then you just put them together into a binary. And then, just like before, you just run it. And this one is much slower than before. So now, only to remember the one before, we were using Goto. So you can, instead of having your code just implementing the gem, you use the one from Goto Blast, which is what we did in the first example. Yeah, I know. And just executes instead of my code, uses the library code, and it's in this case like a bit more than 2 times faster. And now the point here is that if you're using 2 libraries, for instance, that define the same function, the same symbol, for instance, both libraries give you an implementation of dgem, you have to be careful. Well, there are 2 reads for this. You have to be careful in the order you specify the libraries so that it links to one or the other, or you have to use this to use, for instance, your own implementation of gem if you want to use gem, and then exploit the rest of the functions that the Blast library offers you. So if this line, I don't want to get into details. I'm just building a static library. So just putting together, in this case, only one object file. You can put many of them. So we're building a library with just the gem from the reference Blast, which is a non-optimized Blast, and then Goto is the optimized one. So when you compile it, this library includes our gem, which is the reference, the slow one, and then you specify the Goto Blast, which means, okay, all the other symbols you may want from Blast, take them from this library. I may use 3. Oh, yeah, sure. Thanks. Yeah, I was missing that line. So we're building the object files. We're creating this static library for my Blast, and then we just link and generate the executable. Okay. As you can see, it's a slow one. It's using the slow implementation. But if we do this, the compiler will get the dgem from the optimized library and will be much faster. So it depends on what you want to do. You have to be careful either way. Either if you want to use your own code, just make sure that the compiler gets your code and not the library one. If it's the opposite and you really want to use the optimize, just be careful and put it in front so that you don't mess up with your own code. And it's not into the story, yeah.
Okay. When does he use what? When does he use your own code? When does he use the library code?
Here. So, the compiler follows this line. She says main.o needs this symbol, let's say the function dgem. The gem is in both myBLAS and GotoBLAS. So it will follow this line, and the first time it finds this symbol, it will use it. So in this case, this one is specified first. We'll get this dgem. When it gets here, it will ignore it because it doesn't need it anymore. So we'll use this one. If you reverse it, it will take this one, and once it gets here, it will ignore it. So sometimes it happens that you're defining some function that is also in the library because you have your own implementation, and then the numbers are not the ones you expected. Sometimes the problem is that you messed up in the order with the order of the libraries. And just the final one is not totally related, but you may want to use a dynamic library instead of a static one. It's the same Goto, can be static or dynamic. And you just specify directory where the library is, and then
But it's not explain
dynamic.
difference.
Okay. It's just to say that there is a path, the library, an environment variable that you want to set, but we can ignore that. Okay.
Well, you can explain what you do.
Just explain what you need to do, not what it means. Would take. So, if you link to a dynamic library, like in this case, usually with the extension SO in Unix, or most of them, it will compile like this, for instance. You don't get any error. But when you execute it, it might complain because it doesn't find the library, it doesn't know what it is. So if we do, so let's show it here. See, it says, okay, I need all these dynamic libraries, cert libraries, and I don't know where to find this Goto2 library. So apart from the default directories, the system will look into this library, this environment variable, which is not set now. Oh, no, not this one. This one.
So the only difference was you used capital L for the library?
Yeah. The difference is you're actually using a different file, different library instead of the.
But show both lines. In one case, you specify exactly
The file and is the static one. Well, just one. So you have these two, goto.a here. Well, this is the link, but anyway, and the dynamic one. So in this one, yeah, you're specifying the path to the static library like if it were just an object file. Here you say look into this directory, which is libs gotoblast2, and then you give this string, which is it will be expanded by the compiler. It will say, okay, L, I will put lib, and then in the end it will append .so. We'll look for this libgoto2.so, and that's the dynamic library we link to. And it's different the way they handle. The dynamic is not inside the executable the other one is, and so on. There is a lot behind it.
If you guys look in the file trm.c that I uploaded, at the top, I make an example of how to compile with BLAS, and that's a dynamic BLAS. And the second comment is how to compile with LAPAC, and that's a static LAPAC. So I show those examples.
So the problem was it doesn't know where to find it. And if it's not in the default directory, we'll look into this variable. It's not set, it doesn't find anything. But if you do the following, you specify, you give it one value, for instance. No. You say, look for this one. I'm sorry. Now it is set, and then it knows where to find it in this line. It says, okay, now I know what it is. And I can actually execute it instead of getting the error I got before. Yep.
You don't have to do it, but you can do it by with the compilation command, right? You can say, look at that path.
You say it for the compilation, but then you also have to set it for the runtime. So in the compilation, we're saying where it is. So we're saying, yeah, it's in this directory.
Okay.
So that the compiler, the linker, finds it and builds the executable. But then in runtime, it also needs to know where it is.
Okay.
So you have to specify unless it's in a default directory, but otherwise you have to say. This is just pretty simple, just a short example, but so that you can actually just go recursively. This is Spanish, I'm sorry. So the directories with capital letters, these are data structures, and inside of them there is another makefile of specifying how to build the data structures and some binaries and so on. Actually, let me clean. So you have these, so you have 4 of them. So what you can do is you have a makefile inside of each of these data structures, and you can tell make to get recursively into these directories to execute every specific makefile. So you can have a for loop. So I specify the directories here. These are the 4 data structures. And it loops over this directory. And then with the option capital C tells make to get into this directory and execute make this rule simulation. So it will enter each of these data structures, will compile it, and generate all the executables for each different simulation I want to run. And then there is another one to build the report, to build figures, to clean not only the current directory, but also inside every of them, and so on. And if you execute this one, you can see that it says, okay, I'm just entering this directory, I'm executing make, I'm compiling it, I get out, I go to the next one, and so on. And you can do the same for other stuff as well, so just quick sample. That for you to know there is this option. That's about it for the basics of makefile. Just to finish, to put both scripting and makefile just together in a simple one. This is again the code to run the gem many times to to test the performance of the library. You could put these things together in a script, for instance, this example. So you can have some initial step where you say, okay, if the executable the main object, main file doesn't exist, execute make so that you build it, because we need it to run the experiments. If the place where the directory where I will store my figures doesn't exist, just create it. So you set up the test. You can set some environment variables. You can export them. You can specify how many repetitions you want to, how many times you want to run your simulation. This is again the example of this seek command. So usually you want to specify some range of sizes for your problem, for instance. So you go in steps of 500 up to 2000. Again, the back quotes return the string that generates the program. So it gets 500, 1000, 1500, 2000. And then I have 4 different tests combining transpose and non-transpose for gem. So either B is transpose or A is transpose or B or both or none. And all of them do the following. You just specify the file where you want to dump your numbers, and then you create an empty file, for instance this way. You want to create this empty file because if you run it twice, the second time you don't want to append, you want to use the new numbers. So every time you just truncate or just empty the file. And then for this number of sizes from 500 to 2000, I didn't explain this command. I'll do it now. You want a file where it says, for instance, okay, for this size, you get these gigaflops, or you get these timings, this size, this timing, every row, you have one size, one timing. So you iterate and you have, okay, size, and then you will append the performance numbers that the executable will give you. This T command, what it does is, first we print some string, we echo it, display it, goes to the standard output, and with the pipe it's redirected to the standard input of T. And what T does is similar to cat. So you get something from the standard input, it displays it in the standard output, but at the same time it writes it in a file. So you can see the numbers while executing, and at the same time you store them to then plot your figures. And this A means just append it, otherwise it will be overwriting the file all the time and you will lose most of all the numbers but the last one. So this one appends the size, and the second line executes, gets some gigaflop number, and then appends it to the file. And you have 2 columns, sizes and gigaflops. Same for the other combinations. And then if you want, you can automatically also plot them or visualize or anything. Okay. So again, you compile. The make file is just one of the previous ones, nothing different, just using the static gotoglass. And then you may run the test. So this is what T is doing. It's printing the strings that it gets in the standard input, so sizes and timings, and at that same time it's on these files, so that you can use them afterwards to process them, to plot them, to whatever you want to do with it. This would be just a very typical script we use to test code, to test libraries, to test any other project we're working on. We want some performance numbers. So you have your makefile, you have a simple script that just tries different number of threads, different number of size for the problem, different libraries, whatever. You put it together, you submit it to the cluster, and that's it. You wait 1 hour, 1 day, God knows. And that's it for today, I think.